Hello, good morning, everyone. Sincere apologies for the issues. This is 30 minutes behind our scheduled time already. I'm trying to share my screen so I don't waste further time. But I need Engineer Uche, if you're there, if you can hear me, please. I need permission to share my screen.
My sincere apology to everyone. Good morning. I had some glitches this morning. I sincerely apologize. But I will crave the indulgence of Mr. Chima to extend the training by 30 minutes, please, while I record every session. Chima, please go ahead.
Okay. I'm sharing my screen. I'm sharing my screen already. Can everyone confirm that you can see my screen?
Yes, good morning. We can see your screen. Good morning.
You can make it full screen, please. Full, sort of.
Okay, let me just go ahead with the training. Sorry again for this. So today we're going to be starting with the energy and electrical basics. And the reason why we're doing this is just to bring everyone to speed. We know people have different backgrounds. Some have engineering background, some do not have engineering background. However, some have been in the practice of energy, and they see this as an opportunity to come up to speed on the technicalities of what they're already doing. So we deem it fit that would have to start from the basic, and that's why we're doing this. And we crave the indulgence of people who are already far ahead in terms of their knowledge curve, who are already far ahead of what we're going to be discussing today. For people in that category, I really want your contributions as we go along this training. This is going to be a dialogue. I'm only facilitating this. I want everyone to participate actively, and let us all learn together. For the fact that I'm facilitating this does not mean I know it all, or I'm ahead of everyone. In some aspects, some might have, maybe they've done a little bit, more in-depth work, and your contribution will be highly appreciated. So my name is Chima Moneke. I'm an energy consultant with certifications. I'm a certified energy auditor as well as a certified energy manager from the Association of Energy Engineers in the US. I've been doing this for more than 10 years. I mean, well over 12 years now in energy practice professionally. So I'll be combining my knowledge and my wealth of experience, in delivering this training. And I will also want everyone to be part of this. Your feedback, it's highly welcome. As we proceed along the training, there might be need to make some adjustment on the slide if at any point we feel there is a need to make any adjustment just to make it more comprehensive. At the end of it, it's going to be shared across everyone. I know there's already a folder that's been created where you can pull some of these resources from. So every tool will be deposited in that repository for people to have access to. So without wasting much further time, we'll jump in, and we want to first of all understand the concept of sustainable energy or energy sustainability. So at this point, I just want a little feedback, maybe one or two contributions, then we can continue from here. So, but I want to we'll have started with a short introduction. I think it's still necessary, please, because this is the first time we're having this training, and it's important that we understand, the participant, not totally, but at least a little bit of the diverse, participant that we have. So I think we can do that now. So in no particular order, I mean, just unmute yourself and just introduce yourself. Just a very brief one. I mean, 30 seconds, what am I saying? 10 seconds introduction should be fine, please. We've wasted much time, but I think it's very, very important we do this. I mean, we can't just ignore doing this introduction. It's very important, and I think we have to do it. So 10 seconds, tell us your name. You can tell us your background, your place of work, if you want to, and we can continue. And perhaps your location.
Dr. Abdullah Suleiman from GNT Systems based at Tano. Thank you.
Thank you. Dr. Oshoba. I'm a building services consultant. I'm based in Abuja.
Thank you, Engineer Oshoba.
Okay, my name is Femi Adewale. I'm an electrical engineer.
Femi, go. Okay.
A very good morning to all of you. I am attending your lab with Steven. I'm an energy consultant with some World Bank and Statistics project. I'm based in Abuja.
Sorry, you're based where?
I am based in Abuja.
Okay, all right. Thank you for joining us.
I'm Engineer Abdulkarim Musa, an electrical engineer, retiree from with former PACN, then with Baystream Energy. I'm retired now. I'm on my own. I'm in Kano.
Thank you for joining us.
Good morning, everyone. I'm Engineer Samuel Ojo, electrical engineer, a consultant from Abuja.
Thank you.
Good morning, everyone. I'm Engineer Diomi. I'm in Lagos, recently retired with a renewed interest in sustainable energy and
engineering. I'm currently in Abuja.
Thank you.
Working as a software engineer.
Okay, Ibrahim, it seemed there's somebody that spoke before you. I didn't get the person before Ibrahim. Someone spoke before you. I didn't get.
Okay, Engineer Diomi, that's my name. Recently retired. I stay in Lagos. I have an interest in furthering my knowledge in sustainable energy.
Okay.
And solar panels. Thank you.
Thank you, Engineer Denika. Any other person? Okay, I think that will be all. Okay, thank you very much. I mean, I will need like 1 or 2 contributions on what our understanding of sustainability, energy sustainability, or sustainable energy. I mean, just 1 or 2 contributions, and then we'll take it from there. I mean, I just want this to be interactive. I mean, I want to get a feedback. What's our understanding of energy source? Because it's a buzzword now. I mean, when you talk about ESG, environmental, social, and governance issues, we talk about climate change, we talk about decarbonization. All of this comes together and crystallizes around energy. When we talk about decarbonization, about 70% of greenhouse gas emissions are coming from energy. And that's why energy is at the center of all of this. So just about 30% are coming from other sources, but about 70% of this are coming from energy. And so you can't override energy when you're talking about sustainability or global economy. You can't. Energy is an important issue. So what is our understanding of energy sustainability? I mean, it doesn't have to be right. I mean, for me, there's no right or wrong answer. It's all depends on the perspective from which you're looking at it. So just feel free. I mean, let me know what, I mean, you understand. I mean, just feel free, please.
Okay, hello.
Yeah, Engineer Femi, I can hear you. Please go on.
Okay, sustainable energy is about using the energy resources of the world in such a way that our generation does not deprive the next generation of the ability to live comfortably using whatever energy resources is left. And essentially, it's about ensuring that we use energy in a responsible way. We don't waste energy. We encourage cyclic economy, where it is possible to recycle energy sources, and also to ensure that we identify renewable sources of energy and use them. Thank you.
Thank you very much. Fantastic. I think you've said it all. I mean, if anyone has something that is contrary to this, I mean, feel free to, I mean, we want to hear from you, but I think he has said it all. I mean, at the core of this, okay, is somebody speaking? Okay, kindly mute yourself if you're not speaking so that you don't interfere with our conversation. Ibrahim, can you mute yourself? Let me look at a way to do that for me. Can you mute yourself, Ibrahim?
I think the network is not very stable. At my end, I need to ask.
I can hear clearly. Maybe the network is from your end.
Trying to see how I can mute Ibrahim. His voice, the background from his location, the noise from his background is interfering and disturbing our meeting. So we are still talking about the concept of energy sustainability, and Engineer Femi said it all. We have to find a way to use and manage energy so that we don't deprive the next generation of enjoying the same privilege that we have, right? So we don't create energy. Humans don't create energy. Energy is a natural occurrence, and we can only harness and transform energy, but we don't create energy. We are going to get to that, but of course, for the fact that we don't create energy, we have to find a way to use it, utilize it such a way that the next generation coming after us and after the next generation, they still have, the same privilege that we have of energy, access to energy, and not just access to energy, also conserving the environment, because energy somehow also affects the environment. It comes from the environment, it goes back to the environment. If we don't do it properly, it's going to destroy the environment, and it's going to deprive the next generation and the generation that comes after them and thereon of meaningful living. So that's why the concept of energy sustainability is important. And we'll talk about energy sustainability. Two keywords, two things stand out for us. One of them is energy efficiency, and the other one is renewable energy. Unfortunately, a lot of people are familiar with renewable energy, and when it comes to renewable energy, a lot of people are only familiar with solar system, and that's not the only renewable energy that we have. So in the hierarchy of sustainable energy, renewable energy is not the first thing that happens. The first thing that happens is energy efficiency, and which we are going to unpack all of this in the course of this training. We are going to look at energy efficiency in industries, in commercial buildings, even in our homes. We are going to unpack this, and we're going to look at energy efficiency. We're going to look at the technologies of energy efficiency, and then we're also going to look at renewable energy. We're going to look at, basically, we're going to give more attention and focus to solar systems, right? But of course, like I said, the hierarchy of sustainable energy starts from energy efficiency. And what is energy efficiency? Cutting down the inefficiencies, cutting down the losses. How can we assure ourselves that every unit of energy that comes into our home, the kilowatt hour of electricity that comes into our homes, can we actually account for how they are used? That's food for thought. That something we'll have to take away from this basic knowledge of energy. Every unit of energy that comes into our home, can we account for how they were used? So if you can account for it, you will see that along the line, you will see there are inefficiencies. If the light bulb is on in a room and there's nobody in that room, it doesn't need to be on. That is inefficient. The reason of turning on a light bulb is so that you can have visibility. But if there's nobody in that room using the light bulb, it doesn't need to be on. If you leave an air conditioning on in a space that is unoccupied, of what use is that? Except you're trying to use it to preserve something. Maybe you have a storage, maybe a pharmaceutical company that you want to store medicine, or you have food that you want to keep at a controlled temperature, then it makes sense. But if nothing is happening in that room and there's no human being, nobody in that space, and the air conditioning is running, it's a waste of energy. So all of these tiny inefficiencies in our home, if you go to the industry, it's also a lot happening there of losses. And all of this inflates your energy bill. It goes up because you have to pay for it. If you use them inefficiently, you have to pay for it. Especially for those in band A, where the cost of energy is now very exorbitant. And if you're on band B, yes, you might still be able to manage with the budget. But if you're on band A, the gap is so much. On band A, you're paying as much as 200. On band B, you're paying as about 60 something naira or 70 naira thereabout. So you can see the huge gap, right? So it makes sense to first of all curtail and manage the losses. Then you now come down to the next level, which is the renewable energy. How do you diversify your energy sources? Where do you get your energy from? Okay, so if you're getting your energy from a renewable sources, then you're already, practicing energy sustainability, right? So that's what energy sustainability is in a short term. In a short term. So what does energy mean actually? Please, as we progress, if you have questions, if you need further clarification, please call my attention, and I will. Because the way I've structured this and the way I'm going about this, I try to explain it in a way that makes sense. But of course, I know people are at different level. If you don't still understand what I'm talking about, please let me know. Maybe I will frame it in another way and then see if you can catch up with the lesson. So energy is a Greek word. It originates from the word energia. And what it means is activity. It means drive. It means force. Rigor, strength. All of these are synonyms. They're all synonyms of energy, and they all are attributes of what energy simply means. It is a capacity. When your heating energy is being used, meaning you're adding energy. When you're cooling, you're also using energy. In that sense, you're removing heat. So in all of these processes, energy is being used. Now, energy is one of the most important concepts of natural science. Nevertheless, it is very difficult to define in few words. Energy is everywhere, all around us. The fact that I'm speaking to you now, I'm expending energy. I'm using energy to talk to you. Most of you are participating using your laptop or your mobile devices. You're consuming energy. When you talk to me, you're consuming, and it's everywhere all around us. So it's just everywhere. So what are the needs for energy? Why do we need energy? Like I said, energy is everywhere, and we need energy to accomplish so many tasks. In preparing our food, in heating or cooling our homes. For those of us in Nigeria, in Africa, we use air conditioning system to cool our home. For some other people abroad, maybe US, Canada, Europe, and some other places that has cold weather, they heat their homes. All of these are the need or the necessity for energy. For personal hygiene, you pump your water, everything that that you do along the value chain of water, just for cleaning and whatever it is, they all require energy for your lighting purposes, for work. So all of these are the basic needs of energy. Then you go to the industrial sector. Every product you see out there in the market has energy inputs through the production line, transportation, whatever it is. They all need energy, to come out, as a value that you can purchase off the shelf. So there are different forms of energy in different forms. So we have the mechanical energy. Example of a mechanical energy is a moving car, a living frog. Even we as human beings, when you move your body, is a form of mechanical energy. When you walk, is a form of mechanical energy. We have a thermal energy. When you cook your food, when you when ice cream is melting, when your refrigerator is working, all of these are forms of thermal energy. Then you have the visible energy, which is the light bulbs you have. Now, the visible energy is a form of electromagnetic form of energy. And the visible light is only the visible form of that energy. There's what we call electromagnetic spectrum, right? So along that spectrum, you have a visible light. That's the only visible form of energy in this space. You have an infrared radiation. You cannot see infrared radiation, but it's also an electromagnetic form of energy, but you can't see it. It's only visible light that you can see. You have radio waves. You cannot see radio wave as well, you know. So there are other forms of radiations along that electromagnetic spectrum, but you can't see them, but they are all forms of energy. They will have electrical energy, which is very common. This is what we use basically in our homes to power everything. I mean, almost anything in our home: air conditioning system, your TV, your fan, and most of the things, appliances you have in your home are sourced from electricity. So that's what most of us are conversant with. They will have the chemical form of energy. The food we eat is a chemical form of energy. When you strike a match, is a form of chemical energy. And they will have the nuclear. The nuclear is another form of energy. You hear about nuclear power plants. You know, so in those places, there are nuclear activities that are taking place to generate the electricity or the energy from the stations. So these are the various forms of energy and shapes that energy exists, just so that we are aware of, you know, energy around us. Now let us go back to the source. You remember when in my opening speech, I said that we don't create energy. Humans don't create energy, and we don't also destroy energy. We only use energy in the transformation process. I mean, you know, we use energy to transform processes, but in that process of transformation, energy is not created, it is not destroyed. So let us just go back, you know, to the origin of energy. Almost all the energy that we can see around us comes from one single source, which is the sun. You know, so how does energy then move from the sun to different forms and shapes that we are seeing today? So let us just walk through that part. So we know that in our basic sciences, you know, in our elementary school and secondary schools, we are taught about photosynthesis, how green plants, you know, in the presence of sunlight and convert sunlight energy into glucose, right? I can't remember exactly how it was defined, but of course, we all know that the photosynthetic process is a way through which green plants convert sun energy, I think in the presence of chlorophyll or something like that, into glucose, right? So this is how it happens from the first stage, right? Now, what happens from here? Human beings, animals, we all feed from plants, you know, vegetables that we eat, and you know, everything that we eat. I mean, not everything necessary, but in terms of vegetables and green food. Of course, human beings also eat animal, you know, the beef, the chickens, and everything. But of course, this is a food chain. They all originate, they all get their food from green plants. Okay, so now what happens next? In the end of everyone's life, whether the animal, whether the human beings, whether the green plants, when everyone, you know, has, you know, accomplished their mission here on Earth, and then we are committed to the Mother Earth, you know, we go through a transformation process to become crude, what we know today as crude oil and gas. They are all gotten from the decomposition of living organisms, whether humans or animal or plants. That is how crude are formed underneath the earth. Now, this transformation takes millions of years. It does not take tens or thousands of years. It takes millions of years for this, you know, living organisms to transform into that crude oil that we exploit today. Now, because of industrial evolution, you know, the man's need, you know, remember from the creation, I mean, there was nothing like electricity. It was along the line through the through the industrialization process that, humans begins to, invent and innovate and begin to introduce some of these technologies that we use today. And in the early days, they started producing electricity, Now, why all this were happening? They needed a source, to sustain the generation of this electricity and industrial activities, right? So that was how they discovered crude oil. So what that simply means that, look, because of the limited knowledge available at the time, they somehow were able to, extract crude oil from underneath the earth. And then, now this is the extraction of the crude oil. And from there, they are able to process it into different forms of energy. The petrol that we use to run our vehicles today, the kerosene that we use in cooking, the gas that we use in producing our electricity that is going to the grid, the gas that is used to run industries in terms of the steam production. I mean, for industrial processes, they use steam in steam production. All of this are coming from the crude oil, refinery, right? Now, when I say crude oil, I also mean oil and gas. Yeah, because in the process of extracting crude oil, in some instances, you have associated gas that comes with the crude oil. In some other instances, you just have only gas that without the crude oil. But when I say crude oil in this sense, I'm meaning the oil and gas. Now, these are the things that we use to power our economy. And energy is a very critical, component of the economy. You can imagine when with the crisis in Russia and Ukraine started, you can imagine the impact it had on the European countries, because their economy depends on that. In fact, at that point, some of the abandoned coal power plants in Europe begin to come on street. They started going back to some of those technologies because they needed this energy to keep the economy going. So it's a very important discussion around the world, and that's in a sense also now created a problem for the world. Now remember that the sun is already here producing all the energy that the earth needed. Now, by creation, the creator has also made it possible that plants and animals can exist in a harmony. What that means is that human beings breathe out carbon dioxide, CO2, what we know as CO2. The plants absorb that CO2 and generate oxygen. Then human beings take in that oxygen. I want you to understand the balance of nature here, right? But when we started this exploitation, we begin to offset that balance. We started creating more CO2s, by this, extraction of crude oil and then using them on the earth. Now, this crude oil has been sequestrated along the line in the energy, in your journey into the energy field or your energy career. You will hear something about carbon sequestration. Now, sequestration means, the storage of carbon underneath the earth, which originally had happened by a natural means. But because of human need, to power their economic activity, we extract them back to the surface of Earth through, oil drilling, right? We bring them back, and it now leads to so much concentration on the surface of the Earth. And then CO2 is a type of greenhouse gas. What greenhouse gas? What they do is that they trap heat. They trap heat and hold it on the surface of the Earth. And once that happens, it begins to increase the temperature of the surface of the Earth. Right? And that is what we know as global warming. That is what we know as global warming. So the surface of the Earth begins to rise in temperature, and if not controlled, it begins to change so many things. Remember that temperature controls a lot of things. It controls rainfall. It controls, the weather conditions. How things happen. So the moment you begin to, obviously when rain is supposed to come down, it may not come down. At the time it eventually needs to come down, it will come down heavily in a particular region, and it will result to flooding. And it begins to displace people. It begins to destroy properties. All of this are what we know today as climate change. I want you to understand the sequence of how these activities, started and how we got to where we are today. And that's why it's important I create this background. I mean, if anywhere along the line is not clear to you, please ask questions so I can clarify. What I'm trying to establish here is two things. One is energy conservation, the law of energy conservation, that we don't create energy and we don't destroy energy. We only use energy, to transform, in a transforming activities. When you power your television, the electricity that comes into your television is not destroyed in your television. It converts into two things, heat and sound. The sound that you hear from your television is the electricity that is going into your television, that is also part of it is converted to sound. Part of it is converted to heat. If you touch the panel of your television, you feel the heat. That is the electricity that is also going back into the environment. It is not destroyed. The one that goes into your fan, your cooling fan, does not get destroyed. It is used to produce mechanical energy that that rotates the blade, that eventually pushes the air towards your direction. That's one. Two, when you touch the motor, the coil of your fan, you feel heat. You feel that it is hot. That is how the electricity is transformed and sent back into the environment. Okay, so this is how our activities or our use of energy contributes to global warming, and global warming eventually leads to climate change. And that is why the concept of sustainability is so important. And that's why the world, in fact, the biggest threat to the world is climate change. In fact, it's a bigger threat compared to the war and the war that we're seeing around the world. In fact, some of this war that you're seeing around the world is also, caused by climate change, because some people want to have access to some certain natural attributes. They want to have access to maybe natural waterfront. So many things are also the ones we're having in Nigeria, where you find the headers moving from one point to the other. Some of the reason is because the water, and this is also very common around the Sahel, where you have some of the water drying up, and these people need to move. They need to feed their cattle. So all of these are the consequences of climate change. I don't want to dwell so much on climate change. This is not about climate change, but I just felt that it's important to establish that background so that we can, also make more sense of, what we are talking about. I may not read all of this literature here. I already explained them. Energy does not remain in the same form. I've already explained this. You have access to these materials. You can read through them. And then it also helps you to make sense of what I've explained to you. So another thing I want to clarify is energy and power. These are two different things. They're not the same thing. A lot of time, even people who are also advanced in their professionals also mix this up. They're not the same. Energy is different from power. However, they are related, okay, but they are not the same. Energy means capacity to do work. In the science, in the science field, we say that energy is force times distance. And let me explain this a little bit. If a car is stationary, you have a car that is not moving, and you try to push it with your hand, as long as that car does not move, you have not used any energy. You have not used energy. If the car is stationary, but you try to push it to move, as long as it does not move. So what you're trying to do, you're applying force to that car, but there's no distance. As long as it has not moved, then you have not dissipated energy. But once that car moves, then it can be said that energy has gone out from you. Okay? And how you now define that energy is the force you apply to that car times the distance that car has moved. That is a fundamental definition of energy, where you can use fundamental formulas to define energy. But we are going to go into a more simpler form of energy that we all can relate with. Okay, in another sense, power, now I've talked about energy. When you apply force and then plus a distance, that is energy. Energy has gone out from you. But let's look at power. Now, power is the rate of using energy. it's the rate at which you are using energy. Let me use a simple explanation to explain between power and energy. So assuming that you have a horse and then you have a goat, right? And you have 1 kilometer distance to cover. You want to move a horse and a goat within 1 kilometer distance, right? That horse can cover that 1 kilometer distance, maybe say, for example, within 1 minute, for example. I don't know exactly how long it's going to take a horse to cover 1 kilometer distance, but I'm using it as an example. But of course, I know that it's not going to be too far from it. So if it uses 1 minute to cover that 1 kilometer for a horse, then for a goat, it's going to take much longer time to cover that same 1 kilometer, right? But in the end, they will have used the same amount of energy. The horse and the goat will have used the same amount because they cover the same distance. However, the horse covered that distance in a shorter time than the goat. Okay, so in the end, like I said, they both use the same amount of energy, but they both does not have the same amount of power. The horse have a higher power, right? While the goat has a lesser power. So that is why the horse can, cover that 1 kilometer in 1 minute. And then the goats can cover it in more than 1 minute, maybe 2 or 3 minutes. So that is, I just use this as an analogy to explain what energy and power is. So power is the rate. Power is the rate of using energy, all right? So now let me come to the basic term that we can all be familiar with. Power is measured in watts. When you pick up your light bulb, it's measured in watts. So that tells you the rate at which it can consume energy. If you have your incandescent light bulb, it consumes more energy. If you have, because it has a higher rating in terms of watts, some of them at that time were rated 60 watts. So they consume more energy. If you use that 60 watts over 1 hour, then you'll have used more energy. But in today's technology, we now have what we call the LED, light emitting diode. It accomplished the same task of visibility, right? Or creating light, right? But of course, it uses much lesser. And so when you look at your LED bulbs, you will see 4 watts, you see 6 watts, you see 10 watts, right? So what that means is that it's going to consume much less energy over time, right? So now, what is the rate of energy consumption? Now, the energy itself is the power is going to consume over time, and that's what we call energy. So energy is power times time, and it is measured in watt second or kilowatt hour. It's measured in kilowatt hour. Power is measured in kilowatts. So this is the basic units for power and energy. Power is measured in kilowatts, right? Or watts. If you want to convert watts to kilowatts, you divide it by 1,000. Then you have kilowatts. Whereas energy is measured in watt second or kilowatt hour. Kilowatt. So this is the unit of energy, and this is the unit of power. Please let's take note. Let's take note of this. I've seen some people, if they want to, make reference to energy, and they will say kilowatt. And then for me, it doesn't make sense because that kilowatt is talking to me. What I'm saying is power, not energy. But what you meant to communicate is energy. So it's technically it's confusing. Now, there are also different units of energy. If you're working in an industry, so if you're doing an industrial energy audit, in many cases you're not going to be dealing with kilowatt for some industrial applications. You're going to be dealing with energy in the form of kilojoule or megajoule. So if that happens, it's not any reason to get worried. There are conversion factors. So 1 kilowatt hour, like we all know, is equal to 3,600 kilojoule. So if you want to convert kilowatt hour, so from what you know to what you don't know, okay? Or if you're giving kilojoule and you want to convert it to kilowatt hour, this is the conversion factor. So you simply divide by this factor and then you have your kilowatt hour. So 1 kilowatt hour is equal to 3,600 kilojoule. 3,600 kilojoule is equal to 3.6 megajoule, and then you continue in that. So just a quick exercise, I mean, for us here, what is it? Why doing this training? I always recommend people to have a scientific calculator. Even up to this moment, I still have my Casio scientific calculator. In as much as, yes, most phones now have that features of a scientific calculator, but I still kept my Casio scientific calculator because it's more handy for me to just, punch what I need to punch. Does anyone have a, Bernard, what are you doing on our screen? Please, you're writing on our screen. Okay, so please, can we just go through this exercise? It's a simple one. What is the cost of 5 kilowatt? Now, first of all, that's 5 kilowatt, just giving you a hint on how to solve this. 5 kilowatt is power, it's not energy. Okay. So in the end, you're going to calculate the energy and then you're going to convert it to this operation in a year. So actually, maybe this is an air conditioning system that's drawing 5 kilowatt, and this air conditioning system is on all through the year. And what that means is it's running for 365 days for 24 hours. So if it continues, you're going to have 8,760 hours in a year, right? So use this value and convert this to energy, and then convert it to money. If the cost of electricity is 0.1 USD, perhaps this might have been Naira, but let's just leave it the way it is. This is about 10 cents, so 0.1 USD per kilowatt hour. Can you run a calculation and tell us how much, first of all, tell us the energy that this would have consumed, and then tell us the cost of that energy. I mean, can we do this? I mean, this should be done in less than 30 seconds. You can post your answer in the chat if you want to. Ninke has a value, 4,380 USD. Do you have another participant post an answer? I just don't want to take one for it for everyone. At least let me have like 2 or 3. Then we can. I just want to know that, I mean, you're also following the process, and that you understand what I'm talking about. Because essentially, if you need to do an energy audit, there's a lot of calculations. I mean, like I said, it's to be handy if you have a scientific calculator, by your side. It's going to be okay. So I'm beginning to, Yinka, when you posted your answer, you told us the amounts, and then you didn't tell us the energy, the consumption in terms of kilowatt hour. Adeyemi has his answer in kilowatt hour and what that translates into cost. So the reason why this is also important is that so that you can also do some energy. This is a basic energy calculation. You can do this for your home energy calculation. You can look at your kilowatt hour consumption from your meter, and then you look at how much per unit. I've seen instances where people go to buy units. They go to distribution company to buy units. They have certain amount of money and they just pay, and they don't even know the amount of unit they are getting. They don't know the rates, how much per unit. They just buy the load. As long as they see power, they are fine. They don't understand anything that is going on. If they get less value, now this is also important because the distribution company might tell you that you're on band A, or that you're on band A, or maybe you're on band B, and your tariff is on another band. So maybe, for example, you're on band B, and you're being charged for band A unit. Can you imagine the amount of money that you're going to be losing? You're supposed to be paying about 68 or 70 Naira, but you're being charged over 200 Naira. And you wouldn't know. But if you understand this calculation, it will help you to know what you're actually getting. So Fine and good. Let us review what the answer is. Thank you very much for your for all the answers that you've posted. So here's all how. The actual energy consumption is that when you multiply the power by the hours in a year, you're going to get 43,800 kilowatt hour per year. So that is the amount of energy that that device is going to consume for an entire year. So when you multiply that energy consumption by the cost per unit, you will get $4,380. That's what you're going to be paying, as an energy bill for that year. I think for most of what I posted, yes, we are all correct. I'm trying to see if anybody got it wrong, so I will just speak to her. But I think we all our answers are correct. Let me see. I mean, Femi, when you first posted. Said 4,380. Can you hear me?
Yes, we can hear you now.
Yes,
Okay.
loud
I saw
and clear.
something that my network was a bit unstable, so that's why I wanted to know that it can hear me. Okay, so that's it. Let's proceed. So thank you so much for your contribution to the question. So let us look at renewable and non-renewable energy resources. Of course, we already know there are renewable energy resources and there are non-renewable energy resources. Now, what are the renewable energy resources? We have the solar radiation, we have the hydro, we have the wind, we have the ocean-related energy. Now, when you talk about ocean-related energy, you have the wind, the wave. Now, all of these are still nascent. I don't think any of them has been commercially deployed yet. The wave, the tidal, the thermal gradient, but all of them are still, I think they're still at the nascent stage of development and not yet commercialized. But what we know today, that is commercially viable are the solar, hydro, wind. The biomass is basically used in industry and maybe large power systems. Yeah, even at the home level, people that use firewood, that's biomass in a sense, right? And some people might want to argue, how is biomass renewable? Because you can see there's charcoal, you can see there's fire, there is carbon coming, and you begin to wonder how is it renewable? Now let me just explain that a little bit. Biomass is a renewable energy because remember when I talked about how energy moves from the sun through the leaves, through the trees, and then to the animals. So the trees actually convert that sun, which is natural, into what we know today as the biomass. That is the trees and all of that. So when you burn the tree, the net emission of that tree or the firewood that you're burning is the net emission is zero because whatever CO2 that is going out from that firewood or from the forest residue or whatever it is came directly from the sun. So in that sense, the net emission is zero. So it's considered as a renewable, right? They will have the biogas and they will have the geothermal. I may not have the time to talk about these technologies in detail, but in one of our sessions, we're going to talk about the solar system, which is very common. Now we'll talk about the non-renewable energy resources. Non-renewable energy resources are the chemical form of the energy, which is the fossil fuel, the crude oil, and the gas that I talked about, and also the coal. We talked about that are renewable. You can see solar radiation. You cannot exhaust the sun. You cannot finish using the sun. The hydro, the water, you cannot finish this. I mean, so these are not exhaustible sources of energy, and they don't have adverse impact on the environment. So they are considered renewable compared to this non-renewable. And then the uranium, which is a form of nuclear energy, is also non-renewable because the moment you use them, they are used up already. To get them back takes a long time, millions of years to get them back. Now let's also look at energy transfer basis. How do we transport energy? How do we transfer energy from point A to point B? How does it happen? Okay, how does the sun from that millions of kilometers away? How does it get to us here on Earth? How does when you're running your television, the sound is coming from a little bit of a distance, but you can still hear it from wherever you are. So how does this transfer happen? So let us look at it. Basically, there are 3 fundamental ways of energy transfer, right? So the first one is mechanically. And mechanical is the movement of mass by the action of force. And that's why when I told you that when you move your body, when you take a step, when you run, those are mechanical forms of energy. Your air conditioning system is a mechanical equipment. Your fan is a mechanical equipment. If you go to the industry, most of their equipments are mechanical because they involve movement of a mass, right? Yeah, by the application of force. Those are mechanical. So by that way, energy is moved from point A to point B. If you imagine an industry where you have conveyor belts that are driven by motors, right? These are mechanical energy moving, your production equipment, your production materials from point A to point B. The vehicle that you move in, you get into a vehicle, it takes you from your home to your office. All of these are movement of mass by the action of force. And this force is generated by the engine of your vehicle, right? So that is mechanical. Then there's an electrical form of movement. This is a movement of electron. Simply, electricity is a movement of electron. And simply, the mechanical form of energy is simply the movement of mass. Okay, just by their basic definitions. So for electrical energy, it is moved electrically from point A to point B, from the generating plant as far back in the south, maybe in rivers, in Akwa, somewhere around the south, or even somewhere around Kogi State. Wherever you have this power plant, because we operate a national grid. National grid means that these generators are centrally, the electricity are centrally generated and then pushed into a national grid. And then from that point, it gets to every nook and cranny of the country. All of this is happening by an electrical movement. And then the last one is chemical movement of atom. And the movement of atom can be by conduction, by convection, or by radiation. So these are the various forms of energy transfer. Okay, mechanically by the movement of mass, electrically by the movement of electron, and then chemically by the movement of atom. We are going to go more into the chemical form of the energy movement, which is conduction, convection, and radiation. So now let's talk about more. And the reason why we're talking about this, the chemical form of energy transfer, is because you're also going to be dealing with it. In fact, many of us understand electrical and mechanical, but you see the chemical because it's not visible. You can hardly see the process, right? And when you go to the industry, most of the activities that are happening there is either conduction, convection, and radiations. Most of the activities, of course, there's also a lot of mechanical movement going on there, but it's good that we understand, some of these that are, hidden, kind of, because you don't see this conduction, convection, and radiation, but let's talk about them. Now, conduction is a heat transfer by molecular contact, mostly effective in solid material. For some of us that have chemistry background, you already be familiar with this. Some of us that read chemical engineering, you already be familiar with this. So let me explain this with a simple home application. If you have your kettle, if you're boiling water on a kettle, right? Now the heat from the fire, okay? Now you have let me assume that you're using a gas cooker, right? Now you lit the gas and the flame comes out. The flame hits the kettle, which is an iron, right? Now the process through which that heat moves from the flame through the iron, that is through the kettle into the water, is conduction. And that's why it is said that it is mostly effective in solid material. Remember that your kettle, which is the iron, is a solid material, and it is a transfer by molecular contact, right? So it is a movement through most of the times, solid material like iron. If it's a plastic, as long as it hasn't gotten to the point of melting, yes, it can also transfer through that solid, but it's a molecular movement. So once the temperature gets to the point where the plastics begin to melt, then it begins to transform from solid to liquid, right? But let's not go into that. Now that heat transfer by conduction. Now let's talk about convection. Heat transfer through density difference, mostly effectively in liquid and gases. Okay, so now let's go back to the kettle analogy. Now, when the heat from your flame, from the flame of your gas passes through the metal, which is your kettle, into the water, that is conduction. Then from the water, remember, the water that is on the surface of the iron gets heated. Now, how does that water that is heated at the bottom of the kettle, how does it rise to the top of the kettle? I mean, the water that is at the top of the kettle. That process of rising from the bottom to the top is known as convection. So the water from the bottom gets heated, it moves, it transfers, it moves, it becomes lighter. Okay, so it's a density difference. Once something becomes lighter, then it becomes once something becomes hot, it becomes lighter. Yeah, I mean, in that sense, then it becomes lighter. So it moves to the top, and the water that is cold or that is a lesser temperature is heavier. It will now move down. So that density difference is what actually makes water to heat. I mean, the entire water in your kettle begins to heat. At a point, it gets to a boiling point and it begins to boil. Now, that is convection. Let's talk about radiation. Now, when the water begins to boil, and then the kettle obviously becomes hot. If you move your hand, you're not touching the kettle, but if you move your hand closer to the kettle, you begin to feel the heat. That heat that you're feeling is a form of energy, it's energy. But how did it transfer from that kettle to your hand? You're not touching the kettle. There is a gap between the kettle and your hand. In fact, even if there is a vacuum between the kettle and your hand, you still feel that heat. That is what we call radiation. So it's a heat transfer by wave. No material is required, and it can occur in space. That is the thermal radiation, and that's the process through which the sun gets to us here on Earth. It's a radiation. That's why I say solar radiation. If you're in the solar space, you always hear about solar radiation. But that is how the sun, from that millions of kilometers away, that's how it gets to us here on Earth. And then if you have a solar panel, that it strikes your solar panel, and then your solar panel converts it to electricity, direct current electricity though, then you need an inverter to convert to an AC, which is the conventional electricity that we use in our home. We are going to get to that, in some other class, but not today. So what I have just explained is what is displayed on your screen. But however, there's another dynamics to it. Now, there's what we call sensible heat, and that's what we call latent heat. Sensible heat and latent heat. Now, sensible heat is the one. Now, we can sense it by touching the substance directly or indirectly with thermometer. When your kettle is boiling and you take your hand closer, just like I explained for thermal radiation, right? You can feel that the kettle is hot. That is sensible heat. You can actually feel it. Now, there's what we call latent heat. The energy needed to change a substance to a different form. Remember when I said about if you take a plastic is solid, right? And you put it on fire. The temperature begins to rise until it gets to the melting point. It begins to transform itself into something that is called a liquid. I mean, yeah, liquid, but maybe kind of thick liquid. I mean, it's not as liquid as water, but it's essentially turning into a liquid, right? That is the heat that is enabled that is enabling that solid to transform into that liquid is known as latent heat. Now, let me explain it to water. When you, okay, there's a diagram. Okay, fine. This is the diagram that explains this for us. Now, water can change phase. Water can be solid, it can be ice block, it can be liquid, it can also be gas. Okay, when you go to the industries, you're going to be dealing with steam. Steam is still water, but in a gaseous form. That is water in a gaseous form. In a gaseous form, your ice block is still water in a solid form. So the only thing that changes these states, the only thing that makes these changes to occur is temperature. So when you have your ice block, right, and you begin to apply heat to it, at a point it begins to melt. That's what we call melting point. Once the temperature reaches 0 degrees centigrade, you are still adding heat to the ice block, but the temperature will not rise, but you're still adding heat. So what is happening at that time is all the heat that you're adding at that point is used to convert that solid to liquid. So we call it latent heat. When the ice block has completely turned into water and you keep adding the heat, okay, now the water will continue to rise in temperature. Now it's liquid, it's water. It will continue to rise in temperature. When it gets to 100 degrees centigrade, that is the boiling point of water. Every heat that you're adding to that water, it cannot rise above 100 degrees centigrade. So what is going to happen? It's going to convert from liquid to gas, okay? So once it's converted from liquid to gas, the temperature will now continue to rise. There's what, of course, superheated steam, right? Now, these are applicable. Now, the reason why I'm saying some of this, because at some point, we're going to be looking at industrial energy audits. I mean, if you want to, if you work at an industry, I want to conduct an energy audit in an industry, you will need this concept. You need to understand this concept to be able to understand what is happening in the industry and be able to tell where energy is being wasted. That's why this is important. For some of us, we might not, I mean, people who doesn't have interest in doing energy audits, okay? You might seem to you like this, but it is very relevant. You know, at some point, as an energy professional, it's relevant. So let's proceed. Let us look at utilization of energy. Energy use. Utilization means how energy are being used. Okay, so let us start with coefficient of efficiency. Remember, when I talk about the concept of sustainability, I talked about, you know, efficiency, energy efficiency, then you talk about renewable energy. I'm surprised at this point, nobody has asked any question. Does it mean that everyone is following? I mean, that would be nice.
We're following you,
so, okay, thank you very much. So now let's talk about coefficient. How do you measure efficiency? How can you say that this thing is more efficient than this? Okay, if you're driving a vehicle, how can you now say that this vehicle is more efficient than? These are common. These are things that we use casually in our day. I mean, in our day-to-day lives, right? You can say, "Oh, this Ford is more efficient." Why is it that Corolla? People say, Corolla is more efficient than this. It's because you can cover a large mile with a little amount of petrol. That's how you measure the efficiency. So, efficiency is actually the useful energy divided by the energy, the entire. So, the mile that you cover, the energy that you use to cover the mile, we compare that with the entire fuel that you bought. You know, it tells you, you know, some indication of how efficient the vehicle or a process is. We are going to look at it in practical terms here. So we all know, we all use electricity in our house, and we all pump water for it. So let me use water pumping, for example. We all use electricity to pump water in our house. But let us walk back. How does this happen? Where does the electricity come from? Okay, so let us look back. Assuming that the electricity is coming from coal, for example, there's a power plant that generates this electricity using coal. Now you have 100 units of energy that is being put into that coal power plant. It contains 100 units of energy, right? Now, essentially, if this were to be a perpetual working machine, I mean, if this were to achieve 100% efficiency, you're also going to get 100% electricity from this input, right? But it is not so. When this coal goes into this coal power plant, it contains 100 units of energy, electricity, for example. Yeah. So when it is coming out, you're coming out you're only getting about 30 units of the electricity. So 70% of that electricity that is inherent or that the coal contain are lost through thermal losses, through mechanical losses, and otherwise. So the only thing that you're coming out with is 30%. So you've lost 70%. So now you feed 30 units of electricity, you feed it into the grid, 30%. Now, as that electron, remember it's the electricity is simply electron. Remember it's the electricity. So when that electricity moves through the transmission grid and the distribution grid, there are losses. So along the line, about 9% will also be lost. In fact, in Nigeria, it is more than 9%. I think the transmission losses in Nigeria is about 7 to 8%. And then there's a distribution loss, which is also about 8 to 10% thereabout. I mean, the amount of electron that got lost along the transmission and distribution network. And this is happening because of heating, I mean frictional resistance forces. As the electron moves through the wire, there are resistance forces, which we call the ohms, but we'll get to that. So as the electron moves through the wires, there are resistance forces that that leads to heating, and these are the losses. So now, by the time this electricity is coming into your house, into your pump, I mean that used to pump the water, you will have lost 9 units. You've lost 10 units. Now you've lost 70 units. Now you've lost 9 units. Now your pumping machine also has its own losses. So another 10 units you lose another 10 units from your pumping machine, right? Now there is maybe when we go into the industrial, you understand there's a difference between a motor and a pump. A motor and a pump. But let me say this, maybe all together, your motor and your pump, that's your pumping machine as we know it today, have a loss of 12 units. So let me combine this 10 units and 2 units. So let me say 12 units is missing already. So now, okay, this is your pump. This is the motor that actually generates the mechanical power. Now, this is your pump. Now, at your pump level, you lose another 25% of the energy. But essentially, by the time your water is coming out at the end use, you're only having about 9.5 units. Remember, you started with 100 units. Now you're having just about 9.5 units. So you have lost 90.5 units of the energy you started with. Now, if you want to calculate the efficiency of this system, you're going to now say this 9.5, which is the actual energy that you used, or the actual end use energy, this 9.5 divided by 100. And when you do that, what do you get? I want you to quickly do that. 9.5 divided by 100, what do you get? It's a very simple calculation. You still get 9.5, correct?
Yes, 0.095.
Yeah. So in percentage, so the efficiency, I mean, the coefficient of efficiency is 9.5%.
Yes.
But you started now. Let me tell you what's going on in the grid. When you're paying for your electricity, you're also paying for all of these losses. The unit price you pay for your electricity is including the losses along the line, because somebody have to recover this investment. Somebody have to get these losses. So these losses are passed on to the final consumer who is paying for the unit, for the utility. And that is why the concept of energy conservation is important. Now, imagine that you're able to save, if you're able to save 1 unit of electricity that you did not consume, do you know you're saving much more that was wasted to generate that unit? I want you to understand the climate impact of wasting electricity or using energy inefficiently. For every unit that you save, you also conserve or you save all the losses that was, wasted, that was sacrificed to produce it. Right? So it's very important that we start from that point. Let us cut down our losses, manage the inefficiencies. right? So this is how you measure efficiency of a system or efficiency of an energy, electricity, right? So let's continue. Now that efficiency that I talk about, okay, question, go on, please.
Okay, look, I got this explanation straightforward. My question is based on this 70%, 9%, 10%. Because if I look at it, there's nothing left from the 100 unit that is coming. So I just want to know, are you using this percentage as a unit or you are using it as a percent?
Okay, it's in this sense, it translates into percentage, right? I mean, in this sense, it's translated into percentage, not as the unit.
Okay.
Yeah,
okay.
I mean, when you look at this, when you look at the 70%, okay, you look at the 70%, yeah, that's what it translates into percentage. Yeah.
That's clear. Thank you. Thank you.
All right, you're welcome. So then let's look at how the efficiency, I mean, the coefficient of energy, how do we actually, how do we put them to use, right? So in energy management, there's what we call specific energy consumption. Specific energy consumption. So this means that the ratio of energy consumption to the corresponding production quantity. So this is basically applicable for production systems. So if you go to an industry, so for example, let me use Dangote and Boa Cement for example. If Dangote Cement, I'm sure they will have these statistics anyway, because most people who are into manufacturing, this is a key indices that they should have. Not everyone has it, but people who has taken time to optimize their system, they have these informations already, right? So if Dangote is spending, for example, 20 units of energy, let me not say electricity because there are so many components of energy that goes into cement production, right? But let me say he uses 20 kilowatt hour of energy to produce 1 bag of cement, right? So what that means that his specific energy consumption is 20 kilowatt hour per bag of cement. So if he produces 1,000 bags of cement, you can literally multiply and they say, okay, oh, if I'm producing 1,000 bags of cement, this amount of energy I should be consuming or I should be expending. It tells you how much energy you spend for every unit of your production. If you're producing biscuits, for example, maybe Cadbury, if you're producing chocolate, for every unit of chocolate that you produce, for every unit of biscuit you produce, how much energy do you use? It's important to have those things. If as an energy auditor, you go to an industry, these are part of the information that you have to provide to them. And based on that, you can now begin to see. So if you not tell them, okay, if you do X, Y, Z, you're going to reduce your energy consumption. It will translate into that specific use of energy or specific energy consumption. So if Dangote, for example, is using 20 units of energy for 1 bag of cement, and they somehow do an energy efficiency improvement, and then it comes, instead of 20, it now comes down to 15. That's a big savings for them. They have saved 5 units of energy for 1 bag of cement. That's a lot of, so that's how they measure the impact of the energy efficiency measures. Now, if you contrast that, so for example, if Boa Cement is now producing 1 bag of cement and they're using 30 units of energy, who do you think is going to do better in the market? The same bag of cement, Dangote is using 20 units of 20 units of energy, and then his competitor, maybe Boa Cement or Ibeto Cement or which any other brand out there, is doing 30 units of energy per bag of cement. Who do you think is going to do better in terms of market competition? I need a response, please.
That much that will do better. You're using 20 units of energy to produce 1 bag of cement. And the other person is using 30 units of energy to produce 1 bag of cement. It's automatic that the one who is using less units of energy will produce, is saving more, it's saving more than the person using more units of energy.
Fantastic. So that saving can translate into cost reduction for the consumers. You can actually beat down your price in the market. and you're not making any loss. So in terms of market competition, in terms of market competitiveness, if you optimize, and there is this analysis out there about some time ago, Dangote used to produce they used to produce noodles. So at a point, they could not compete with Indomie, who is already the dominant in the market. At a point, they sold out to Indomie. They sold their facility to Indomie. If you check, if you go, we're going to see all that details. So what actually happened, based on the analysis that I read, I saw that, Dangote, the way Dangote operates is that they try to optimize all their resources. So they try to eliminate inefficiencies in their systems. And it makes them to beat market competition, right? But Indomie more like, kind of copied that pattern. Indomie came into the market, optimized all the systems. So when Dangote came in, there was nothing for Dangote to optimize. So Dangote could not beat Indomie in the market. And that's how market works. That's how market competition goes. If, for example, because Indomie, they also have their own power plant. They're also generating their own power. Dangote, if you look at his factories, most of his factories, cement, they're producing their own power. They're not buying from the grid. So they optimize their system. They make sure that they can compete in the market with anybody who comes into the market in terms of price. So they optimize everything. So when Indomie came into the market, they also optimized everything. So when Dangote came, there was no inefficiency for them to optimize to beat Indomie in the market. And what happened? They couldn't compete and they sold out and they exited that market. So efficiency is very critical in businesses. You have to optimize all your resources to make sure you're getting the best value out of it. If you go to industry or business, they have human resources, but you can hardly find maybe energy. Okay, you have human resource manager. You can hardly go and you see energy. Most of them hardly have energy manager. It is now that it's becoming, people are now beginning to realize that it's a significant part of their cost. People are now beginning to, integrate or convert some of their technical staff into an energy manager. And that is also another value for people who are also going through these programs. Eventually, if you continue in this trend and you obtain your certified energy manager, it opens up a lot of opportunities for you. Or you obtain your certified energy, you become a certified energy auditor, it opens up a lot of opportunities for you. That's why we're also sharing this knowledge and experience. I've been involved in so many industrial energy audits. So I can tell you from experience what is going on. So now there's another, these are energy indicators. There's another one which is called energy intensity. Now this is basically maybe at a higher scale. So energy intensity is the quantity of energy required per unit output or activity. Example, GDP. So the way you also measure the GDP of countries is based on the amount of energy input, energy resources that they have expended to generate that level of GDP. Okay, and what that means is so that using less energy to achieve the output reduces the intensity. And I'll give you a typical example. I don't know what the statistic is right now, but I know about 5-6 years ago, there was a statistic that Nigeria uses 40% more energy per GDP. 40% more energy. You can Google it. You can get some of these things are out there. I mean, so I think this study was done by GIZ and some other development partners who are also supporting the industry. Nigeria spent 40% more energy per GDP compared to its peer country like Indonesia, Bangladesh. I mean, those other countries that are at the same scale, at level with Nigeria. Nigeria, however, spent 40% more energy. What that means is that you cannot compete with production from those countries because your energy input into the production or into the activity is higher than what those people are also doing. So these are the indices, how you measure, energy, whether at an industry level, at business level, or at a country level.
Sorry, instructor. Can I just ask a question? Is it
okay? Please go on.
Could it be possible for us? Could it be possible for us to also say in comparing United States of America and China, if you look at the production, the energy intensity of the Chinese is far less than the energy intensity of the Americans in terms of GDP. But the output is, I don't know, maybe I'm trying to say, is it possible to say that the energy intensity used by the Chinese for the same production is far less than the energy intensity exerted by the Americans to do the same? Although the GDP of Americans it seems to be higher than that of the Chinese. I don't know whether you understand what I'm trying to say.
It's not very clear to me, but the way I will also want to respond to when you look at these two big economies, China and America, the GDP of America is still bigger than that of China, right? But are you saying that the energy intensity of China is less than that of America?
Yeah, that's what I'm trying to say, that the energy intensity of the China, because if you look at the definition of energy intensity, it's the quantity of energy required. For the Chinese, they have more population than the Americans.
Of course.
If we now put the energy requirement together, so it means that the energy requirement for the Chinese is actually higher than that of the Americans. That's what it means. Because they use more P.
No. If you look at the energy intensity, if China has lesser energy intensity per GDP, what it actually means that they are spending less energy, for every GDP of the economy compared to America. That's what it simply means.
Okay, I get you.
However, there are other factors that are driving the productivity in China, and which we also must admit that part of what also adds to the energy intensity. So, for example, is scale of production, right? If you have an equipment and if you have an equipment that is meant to perform at 100%, okay, let me use your diesel generator, for example, which is still in the realm of energy that we're talking about. If you're using your diesel generator and you have 100 kilowatts, you have a 100 kilowatt generator, and you're operating it at 40% of its capacity, right? And somebody else has the same capacity of generator and is operating at 70%. Do you know that the cost on that person who is operating their generator at 70% will be much less than you that is also operating your generator at 40%? The same capacity of generator, right? So your load factor has a lot to do with it. So I think if you export this analogy to the GDP, it also makes sense. And because one thing I know about China is that scale of production. China produces for the world. And that has also been an argument I had with one of my colleagues some time ago. We were talking about, establishing some of these factories in Nigeria. What you go to do in China, why can't it be done in Nigeria? Yes, it can be done in Nigeria, but it's going to take time to, to gain that scale, because China will still be cheaper. Somebody can go to China and order. China produces for the world. The same product that's shipping to Nigeria, they're doing it with the same production machine, and they're shipping to America and they're shipping to other places. In as much as maybe there will be variation in terms of quality, but the same production machine. So the scale, the higher the scale of production, the lesser the cost on them. So there are other factors that lead. So, but we are not talking about economy here. Let's just limit it to the energy, where we want to explore. Okay, thank you for the question. Yeah.
Energy drives the economy anyway.
Sorry?
It is related. Energy drives the economy.
Of course, yeah, true. So let's go to electrical energy. So let's go into electrical energy. We might not exhaust this because of the little challenge we have, but however, wherever we stop, because I don't want to drag this. I know a lot of us have schedules for the weekend. So when it is 12 o'clock, we're going to round up and we'll continue next week Saturday. Hopefully we'll be able to cover up. But let's go into electrical energy. I'm sure a lot of us also understand electricity, but we're going to dive into a little bit of what actually makes up the electrical energy. So what the basics of electricity? So electricity is the electron that you see is made up of two things, basically two things, voltage and current. Voltage and current. So voltage is what pushes the electron. So the electron essentially is the current. What we call electricity today, I mean the electron basically is what we call the current. So voltage is a force that pushes the electron through the wire. So this is what pushes electricity through a circuit, or we can also say is a driving force. Now the current is what is pushed through pushed by the voltage. That is the flow. Now what we consume in our homes is the current, not voltage. And let me give you a typical analogy of a water and a pipe. So when you have a water pipe and water flows through the pipe, before that water can flow through that pipe, there has to be a potential difference in pressure. It's either there's a potential difference by height, or there's a pressure from a pump that is pushing the water through the pipe. So that pump, that force that is pushing the water through the pipe is what we know as voltage in terms of electricity. Now the water itself is what you consume. That is the current. A lot of times people say you have low current. I mean, it's very common, especially when you have a transformer that is far from your house. By the time the pressure, that is the voltage, it gets to your end, the voltage will reduce. So the current that you're getting is not, you're not saying you have low current. I mean, essentially what you have is low voltage, not necessarily low current, it's low voltage. But I mean, that aside, so I hope with this simple analogy, we understand what voltage and current is. Okay, so electrical power is when voltage and current works together to do something useful, such as turn a motor or light a bulb, to light a lamp, right? Then you can say that maybe electrical power has been used, or electricity is in use. So electricity is basically measured in watts, right? So what is watt? Watt is voltage times current. Now current is measured in amperes, right? So watts, which is a unit of electricity, is equal to voltage times current, which is amps. Now there's another factor to it. There's what we call power factor. Power factor. Maybe after this we are going to go into different types of power. We'll talk about apparent power, real power, and then the other one. I mean, there are about 3 of them anyway. So this is the unit of electricity. Voltage, watt is equal to voltage times amps times power factor, and that's what you have your real power. Yes, please.
Watt is not the unit of electricity. It is the volt and the amps that are the unit of electricity. Watts is the unit of power, electric power.
Yes. Yes, but power is also So what is the difference between power and electricity? Because for me, electricity is a form of power.
Yes, but when you say watt is the unit of electricity, that's not very correct.
It is
the unit of electric power. So there are other units, voltage, which you already defined, and amps, which is already defined. Watt is actually across several disciplines. Watt is also in mechanical, not only in electricity.
Thank you very much for bringing it. In fact, if you don't say this, I was still going to say it somewhere down the line, because down the line we are going to begin to see kilowatt mechanical. You will see kilowatt mechanical. You see kilowatt chemical or kilowatt thermal. Just like what you've just said now, watt is not just only electricity, it's power. Thank you very much for bringing that, right? You're absolutely correct, right?
I want to make some contribution to that. Can I make some contribution to that?
Okay, please go.
What is more related in terms of power to electricity? While in mechanical, we have thermal, we have horsepower, and a lot of them. Most often than not, what is related to electrical power? Thank you.
You said most often than not, it is, right? But it does not mean that that's all. Like I said, watt or kilowatt is also related with other forms of power. when you are doing some energy analysis, it's often required that you bring all your units to the same base unit. So if you want, remember when I talked about Dangote manufacturing cement, and I say, okay, the unit of their energy is maybe 20 kilowatt hour. That does not mean that it's only electricity. There are also different forms of energy in terms of thermal, mechanical, whatever it is, but you have to convert them to a base unit, and that's your work as an energy auditor anyway. You have to convert everything to a base unit, you know, to arrive at your final specific energy consumption, right? So, yeah, what?
Sorry, sir. Sorry.
Okay.
Sorry, sir. Can I just say something? You know, in mechanical, of course, there's the use of wattage, but it is always used in joules. So if the joules is converted into watts, you know, it is just like you said, you must unify your units in terms of energy auditing. So if you get the joules, you convert it back to watts. You get so that you can have a uniform approach to the energy that you're trying to work on, which is what you are trying to say, sir. Just to clarify the
yes, that is the whole essence. So for all of this, there's a conversion factor, and the conversion factor enables us to move them from different units to a base unit, if you want. I mean, in that sense, right? So it's absolutely correct to say that. I mean, watt is not only for electricity. You can also use watt for power generally, whether a mechanical power. I mean, there are conversion factors. So, but let's not now. If you need to, I'm talking in practical terms. If you go to out there to conduct an audit, if you want to do your analysis, I'm saying it because I've done a lot of this analysis. When you go into your certified energy management, there's a place where you begin to talk about what do you call it again? I mean, it's end user. I mean, I'm trying to remember the exact time, but I mean, let me not bother us with all of. But the point I'm trying to make is that when you get to that point, you find out that you have to begin to unify all your energy into a single base unit so they can compare apple to apple. That's the point I'm trying to make. But let's leave that aside. So let's move forward. So watts can also be defined as VA, voltage times current. You know, just like so in some instances you might see for these smaller size inverters, you know, you might see maybe 500, maybe 1000 VA or 500 VA, or I mean, in that sense, right? So it tells you the power, or I mean, the capacity of that inverter or whatever it is, especially generators. So you see a generator is in kVA. kVA means that you're not dividing by 1000. It tells you the power or the power capacity of that generator, right? So remember when I tell you that power is the rate of energy use or rate of consuming energy. It tells you the rate at which that generator can produce certain amount of energy for you to use. Let's move forward. I think okay, this is we are not going to single phase and three phase electrical system, but I think it's already 2 o'clock. I don't want to stress this. We're going to continue here. Maybe we'll come back on next Saturday. I'll just refresh from this electrical energy, and I'll continue from here next week Saturday. And once again, I want to apologize. Yes, sir.
Please, at the beginning of the lecture, you told us that the 30 minutes lost, that you are going to compensate us for it. So we need the 30 minutes now, please.
No, my problem is that some of us already have programs for today.
No, we are free. I want to believe my colleagues too are free.
No, some of us have weddings. So.
Okay, you have weddings.
Our wives are waiting for us at the altar.
Okay, all right. No problem.
I'm saying this from experience already. You know, so I know people have programs or people have plans for today. So let's not, you know. But the point we are going to cover all of this. Don't worry. We are going to cover everything. I mean, we'll continue from here next Saturday. We're going to cover all of this. I promise you that. So thank you very much for your active participation, and I really enjoyed the conversation. I mean, it's a dialogue, so I really enjoyed it. Thank you very much. We're going to stop here for today, and next week Saturday we continue from here. So I don't know. Do we have any feedback, comment? I mean, so before we end it here.
Yes. Thanks for your lecture. My question, or probably a contribution, is regarding